Trees are great for classification, but they're not the only technique we have available to us, not by a long shot. Let's get out of the trees and meet our neighbors. Welcome to this video on classification. My name is Kevin Fiesel, and I'm the proprietor of Galaxy Services LLC, a consulting firm which specializes in work all across the data platform space, especially SQL Server. In the first several videos of this series, we have focused on tree-based classification algorithms, including CART, Random Forest, XGBoost, and LightGBM. The reason we have focused on tree-based algorithms so far is they have several useful properties in that they are effective in terms of model quality, they tend to give us results fairly quickly, and they're easy to understand. But there is a wide world out there other than trees, so let's start looking at it in the classroom. The first non-tree algorithm we're going to cover here is called k-nearest neighbors, or KNN. This is a spatial algorithm, and there's a spatial intuition behind KNN. Data points that are closer to one another are more likely to be related than those further away. The algorithm itself is simple. We start with a set of data that includes labels, so we have the actual classes for these data points. Then, when it comes time to classify a new data point, we find the k nearest labeled data points using some distance measure, and we choose the plurality or majority class among those k data points as our new point's class of choice. Now it's in our collection, and so we can repeat the process with the next data point and iteratively work through this until we've finished the job. Here's a simple example of it in action. Let's focus on the left-hand new dot and say that k equals 3. For each new data point, we find the 3 nearest labeled data points. Now, I've helpfully marked those as 1, 2, and 3 respectively. We can see that for the left-hand dot, all 3 data points are green, meaning that we would label this new dot as green. Meanwhile, for the right-hand dot, I've labeled the 3 nearest data points to it. 2 of them are orange and 1 is blue. This is a bit more of a challenge than the first example, but we'll go with orange because there are more oranges than any other color in our k nearest neighbors. Incidentally, there is another bit of intuition here. The more spread we have in terms of neighbor classes, the less certain we should be that we've got the right class. For our newly minted green dot, I'm pretty confident that this one actually should be green. But for our new orange dot, there is a reasonable chance that it really should be blue. We'll go with orange as our guess, but we can expect the probability that we're wrong to be a bit higher due to this disagreement. Now, k-nearest neighbors is a beautifully simple algorithm, so you might wonder, why don't we use it more often? Well, there's a reason for that. It's called the curse of dimensionality. It's a simple reason. I mean, I guess it's a complex reason, but, it's simple. It's a simple, complex reason. Just leave me alone. So, all right, what is the curse of dimensionality? The basic idea here is that the distance-based classification algorithms are susceptible to bad results when you introduce irrelevant attributes. Let's take a moment and talk a little bit about classification's fancier cousin, regression. With regression techniques, we are essentially looking to solve a mathematical equation where we have the input features and we want to weight and combine these features in such a way that the output is our prediction. Linear regression is the easiest of these regression algorithms to understand. This is a simple example of linear regression. We have our input variables, x sub 1, x sub 2, and so on through x sub I. For each of these, we apply some weight, alpha sub 1 for x sub 1, alpha sub 2 for x sub 2, and so on. We also have a value for the y-intercept, alpha sub 0, and we have an error term to handle any mistakes in our calculations, epsilon. Let's suppose that we normalize each variable x, such that x always falls between 0 and 1. That will make the thing I'm about to say next a little easier for me to say, though it's not absolutely necessary to drive home the point. So what happens if we have, say, 50 features in linear regression? Well, the most important features will have the largest weights. Let's suppose x sub 17 and x sub 23 are the two features that drive this formula. In that case, their weights are going to be much higher than the variables that do little to nothing for the regression. This means that adding superfluous features to a linear regression doesn't really hurt anything in the end. There is a very small marginal impact, and there's some possibility of multicollinearity or something else affecting the calculations, but again, if they're superfluous, there's going to be a very small impact. Now for classification, there can be a big impact. I've got a one-dimensional plot here. It's a number line, and I have some black dots representing data points. We can see that there is a good amount of noise. So let's introduce a second dimension and turn that into a 2D plot. Now we can see two clusters forming. It turns out that this second dimension was very helpful in separating the two clusters. And let's also say that empirically, this is exactly what we're looking for, and we have a really good model with these two dimensions. But let's add in a third superfluous dimension. We're going to say that it's something totally irrelevant for the purposes of classification. But what we have done is, for one of our two clusters, we've spread out values along that third dimension. That makes it harder to see these points as a single cluster. Even worse, some of those points in the third dimension are close to the mass of the other cluster, so a k-nearest neighbors approach may misclassify those data points as a result. That is the curse of dimensionality. By adding additional irrelevant features, we can make it harder to classify things correctly. So what can we do about it? Well, there are a few techniques we have available to us to mitigate the impact of the curse of dimensionality. First, we can perform feature weighting, similar to regression. The idea is we apply a weight to each feature. We can adjust those weights according to classification error and continue until we have achieved an acceptable level of accuracy. A second option is to perform iterative removal of features. We figure out which single feature has the highest impact and remove it from our classification. We keep doing that until we reach some cutoff point. Then, take all those features you dropped, and those are the important ones that we're going to have in our actual model. You can take the rest of the features and ship them off in a rocket toward the sun. A third option is to perform gradient descent on our problem, iteratively shifting those weights and training the weights using cross-validation. In practice, you may be familiar with a concept known as uniform manifold approximation and projection, or UMAP. This is a technique that combines k-nearest neighbors and stochastic gradient descent, helping us minimize the impact of less important features. And UMAP actually leads us to another natural option. Whenever you think about having too many features of low importance, one idea would be, let's perform dimensionality reduction. And UMAP is actually a dimensionality reduction technique. But it's not the only one. So for example, if we used something like principal component analysis or linear discriminant analysis, PCA or LDA respectively, on our dataset, we could narrow down to some small number of synthetic features that capture the information from our broader set of features. It's harder to interpret the results of a PCA calculation, for example, but it can lead to a viable solution. Now that we've talked a bit about the curse of dimensionality, let's go to a demo and see k-nearest neighbors in action. Up to this point, I've been using a dataset of people who have had heart attacks. Now I'd like to switch things up a bit and use a different dataset. We'll still focus on the scikit-learn library, but we will get the k-neighbors classifier from sklearn.neighbors. My starting point here is to find the 3 nearest neighbors, but you could certainly increase that number if you'd like. I should note that you'll probably want to keep the number of nearest neighbors odd, as that will guarantee a result. If you set it to an even number, you might end up in a situation with no answer, and that would be a really bad outcome. Our dataset is a campus recruitment dataset. There's a header row for this dataset, and we'll set the label to status and have everything save for status and salary and SL number as our inputs. Now let me explain what's in this dataset. This particular dataset looks at 215 people, capturing some demographic information as well as their college degrees and scores. Then it asks the question, did this person get placed for a job? If so, what was the salary? If a person was not placed for a job, the salary is not a number. If we're looking to solve a regression problem, that salary column could be a really good label for us. But we are looking to solve a two-class classification problem. And the problem with including salary here is that if the salary is a number and is above 0, we already know the person has a job. So we have to get rid of that column from our set of X. Also, if we have a new student who's about to graduate, we won't know the salary at that point anyhow. So if we wanted to use this to predict placement rates for new students, we couldn't actually use salary as a feature. Finally, the SL number column represents a student ID and is therefore not helpful to us in classification, so we'll drop that column. Something else that's new in this is that we have categorical variables like gender, degree, work experience, specialization. In the heart attack dataset, every feature was numeric, making it easy to work with that data. Now we actually have to do a little bit of prep work. We need to transform every categorical feature into a numeric feature, as all of our classification algorithms expect numeric features. The technique we'll use to do this is something called one-hot encoding. The idea of one-hot encoding is that we pivot the categorical data such that every categorical value gets its own feature. For example, the gender column in our data frame has two possible values, M and F. We'll create two new columns, one where gender equals M and one where gender equals F. Then, if our original data set included a value of M for gender, we'd set that gender equals M value to 1 and the gender equals F value to 0. If our original data set included a value of F for gender, we'd have gender equals M set to 0, gender equals F set to 1. If we get something other than M or F in our actual data set, both columns would be set to 0. We need to do this for each of the categorical features, but let's check how many categorical features we have using the dtypes attribute. If I look at the outputs, I can see 7 categorical features that apply to X. Gender, SSC underscore B, HSC underscore B, HSC underscore S, degree underscore T, E-test underscore P, and specialization. These are the ones we need to process, and to do that, I'll use the one-hot encoder class from sklearn.preprocessing. The first thing I need to do is instantiate a new encoder. Then, let's get only the object data types from X and save that as X underscore object. After that, we'll fit our training data to the one-hot encoder preprocessor, so it knows what options we have available. The transform function converts my categorical variables into a series of zeros and ones, and I can put them together in an array. Finally, I'll get the feature names using the getFeatureNamesOut function, passing in the base name of each feature. That gives me a total of 16 features, one for each categorical variable's unique values. To this list, I'll concatenate my set of 5 floats and call that final output X. Taking a look at the shape of X, we can see 215 rows and 21 columns. If you'll recall, I started with 215 rows, but I had 12 columns for X. This tells me there's not a lot of varieties in these categorical variables, and in actuality, each one has either 2 or 3 possible values. And if I look at X, I can see the full data frame, including the 2 values for gender, the 2 values for SSC underscore B, and so on. For our labels, we want to use a simple label encoder. The label encoder gives us a new value for each value in our set. In this case, the defaults will work well for us because a placement status of placed gets a value of 1 and not placed gets a value of 0. This means that our confusion matrix will be a little easier to understand than in our heart attack situation, and I don't have to get into verbal gymnastics around the positive and negative outcomes. It turns out that the normative labels for this dataset comport with the positive labels, so negative means not placed and positive means placed. Hooray for us, I guess. I am next going to split this dataset into training and test components, exactly as I did for the tree-based algorithms. We can see an example of how x_train looks, and we see it's still a data frame with 21 columns. Fitting is simple if you followed along in this series. The code looks exactly the same as any other scikit-learn classifier. And now that we've fit a model, let's see how we did. First, I'll show the accuracy of the model. And it looks like we were correct about 81.5% of the time. One note here is that the values will be pretty stable between model runs because I fixed the random state for which rows are part of training and which are part of test. Also, k-nearest neighbors itself is not a stochastic algorithm. It is a deterministic algorithm, and we make 0 choices at random. The only instability we might see is in how we slice our training data. Now let's take a look at the confusion matrix and see how it did. We can see that, looking at each row, we found 13 of the 21 unemployed students and 40 out of 44 employed students. That's a recall of 62% for unemployed students and a recall of 91% for employed students. Meanwhile, we predicted 17 students to be unemployed, and we got 13 of those right, giving us a negative class precision of 76%. We predicted 48 students to be employed and got 40 of those right for a positive class precision of 83%. I can tell you up front that these are not bad results, but there are only 2 ways of saying that a result is good. The first way is we negotiate what that threshold should be with some business decision maker, and we meet that threshold. Then we can say the outcome is good enough. The second option is this model performing better than other models from other algorithms? In that case, it may or may not be good enough, but it is good relative to its peers. Well, the biggest, baddest peer in this space is usually XGBoost, so let's see how it performs on this same dataset. I've chosen some weird-looking hyperparameters for this estimation, a max depth of 2, 101 estimators, and log loss for the evaluation metric. I've also set the random state to a fixed value so I can talk specifically about this outcome. When I run predictions and return the accuracy score, we get back a value of 87.7%, which is better than our 81.5% for k-nearest neighbors. I messed around a little bit with parameters and didn't immediately find a better result, but there is a chance that you could find some superior combination of hyperparameters. Nonetheless, let's see how this confusion matrix looks. We did a better job at finding students who would not receive job placements, getting 18 of 21 correct, or 86%. We also got 39 out of 44 job placement students right, for a positive class recall of 89%. About the only measure which isn't great here is negative class precision. We predicted 23 students would not have jobs, but only 18 of those predictions were valid. Still, I would call these good results, pending a discussion with the business decision maker. So what's the moral to this story? Well, don't forget about non-tree classification methods, but even though you should keep them in mind, there's a reason we reach for XGBoost, LightGBM, and Random Forest first. That was our overview of k-nearest neighbors, with an assist from XGBoost at the end. K-nearest neighbors is usually not an algorithm I think a lot about when performing classification, but in the demo, we saw it perform nearly as well as a fine-tuned XGBoost, and it even did a slightly better job at predicting when people did get jobs after graduation. Also, I want to take a quick moment and talk about the importance of pre-processing. In an earlier version of this notebook, I kept SL number in and mistakenly one-hot encoded the numeric features as well as the categorical ones. Doing this caused the accuracy for all of the classification algorithms I tried to drop considerably, on the order of about 10 percentage points. Yeah, it was dumb, but it's an easy mistake to make when you're not thinking about it or you don't understand how the functions work. Data processing is an enormous part of data science, and even though I'm not spending a lot of time on it in this series, it is absolutely worth digging into the data, understanding how your pre-processing functions work, and understanding what the results look like before you perform model training. Okay, sidebar aside, in the next video, we're going to talk about an algorithm with a slightly confusing name, but a lot of power behind it. We'll have links and show notes in the description below, and until we see each other in the next video, take care.